Welcome back. During our last session, we discussed and we analyzed the actual transformer, an ideal transformer. If you remember from the previous session, from the previous lecture, what we've done is we introduced the transformer importance to the circuit, to our power system, and then we studied the actual ideal transformer condition and we did an example regarding an ideal. Today, we are going to study the practical transformers. If you remember from the previous lecture, we defined 4 points that set the boundary of an ideal transformer. Point number 1, an ideal transformer has no resistor inside the winding. R is 0. In a practical transformer, the winding has a resistance R, which means now I have I squared R exists. If you remember, the permeability mu of the core previously in an ideal transformer was infinite. Now it is not infinite, it is finite. So it has a value. So therefore now the reluctance R will have a value. More into the ideal transformer, we said that the flux phi is enclosed within the transformer boundary. In a practical cases, we do have leakage. We do have leakage. So phi, the flux, is not confined within the transformer. And number 4, previously in an ideal transformer, we said you have no core losses. In a practical transformer, we have 2 types of core losses, real and reactive. So we have number 4, we have real and reactive power losses within the core, within the actual core of the transformer. These 4 elements determine the boundary of the practical transformer. Same, these 4 elements, the resistance, mu, the flux, and the core losses determine the boundary of an ideal transformer. Now, if we take all these informations, for me as an electrical engineer, I need to represent this in a circuit. How do I represent this in a circuit? Let's see. Okay, let's have a look. Now, this is my transformer. From the circuit of the transformer, I can see that my transformer has primary winding, secondary winding. So, because I have winding now, and it's a practical transformer, I have this. This represents the resistance and the inductance of the primary windings. So this known, I can call it R1, this is JX1. These due to the wires. You know, every wire can be represented by resistor and L, inductor. What we discussed previously, that we do have losses. We do have a core losses, which is represented by real and reactive losses. This can be represented by a shunt losses, which is I can represent it This is called, I want to call it R core. And this is due to a magnetizing system. I want to call it JXM. This then, I can represent this. Let me move this side. On the other side, I have second winding. The second winding, I will have R2 JX2. This circuit, from electrical point of view, from electrical engineering point of view now, I have a circuit. This is the primary side. And this will be the secondary. This, I can call it I1 or I primary. This will be I2 or I secondary. This will be V1 or V primary. This will be V2 or V secondary. So now I have a circuit where I can physically perform normal circuit analysis. One more element. Remember this A, which is N primary, N secondary, and I have A. A is equal to N primary divided by N secondary. If you remember what we did previously into an ideal transformer, I can take this Z to the primary side, because this Z seen from the primary side, all I have to do is multiply it by A squared. So in reality, I can go ahead and represent my circuit again by doing this. That's R1, JX1. This will be A squared R2, A squared JX2. This will remain the same. And that will be the one. So what we've done is, we represent this impedance on the primary side by multiplying by A squared. That's exactly what we proved during our last lecture, that the impedance on the secondary side seen from the primary is presented by A squared Z. In a practical, if you remember when we first mentioned that nowadays the transformers is almost 100% efficient. So these values can be neglected into a real practical and advanced transformer. So therefore, I can represent my transformer by the followings. I can represent my transformer by having as seen from the primary side. This will be R1 plus A R2, and this will be J X1 plus A squared J X2. By neglecting the effect of this shunt and losses. As you saw previously, our advanced technology into transformers allow us to have almost 100% efficient transformer. So therefore, the core losses in respect of the total power of a transformer can be neglected. And now, let's take a moment and we will do one example. Let's take a moment and we will do one example. The example that we're going to do today is example 3.2 from your book. So if we all can go to example 3.2. In our example, we have a single phase two winding. We have 20 kVA. We have 20 kVA single phase winding, 480 to 120 volt. During a short circuit test, where rated current at rated frequency is applied to the 480 volt winding. With 120 volt winding to shorted, the following reading are obtained. So if I go back and I sketch my what they said on the winding 2, I applied a short circuit. That's what the book said. So I applied a short circuit on the 120 volt winding. I obtained V1. When I applied, I have V1. These are the reading. V1 is equal to 30 volt. 35 volt. P1, that's a 35 volt. P1, it's a 300 watt. During an open circuit test, where rated voltage is applied to winding 2, with winding 1 is open, the following readings. So now what will happen is, I have this, the second test. I have in here, I have an open circuit on this side, and the following were read. I have I2 and I have P2 were measured under open circuit test, and I have 12 amp and 200, 12 amp, and I have 200 watt. 12 amp and 200 watt. So the first question from the short circuit test, determine the equivalent series impedance referred to winding 1. Neglect the shunt admittance. So let's explain it one more time. I have a single phase transformer. I performed a short circuit test and an open circuit test. I applied a voltage, rated voltage conditions. I apply voltage in E. I short circuit the secondary, and I end up with V1 and P1. I measured the voltage and the power from the primary side. Then I disconnect the circuit. I have an open circuit test. I applied a voltage source in here and an open circuit, and what I did is I measured the current going in and the power going in. The first item I need to do, the first question is, from the short circuit test, I need to find the series impedance. I need to find Z of the transformer. This is very easy. If I use the circuit that I actually determined before. Let's sketch the circuit. Let's sketch the circuit of a practical. If you remember the circuit that we did for a short circuit test, is basically, I have this. let's get a different color pen, and I created here a short circuit. This is R equivalent, JX equivalent. From the previous slide, we know that R equivalent is equal to R1 plus A squared R2. Same for the X. We know what's X. Now, we know that this transformer is, remember this, 480 to 120. Now I have a voltage. I have the voltage, which is, I have a voltage applied to D. What happened is, if you remember, said during a short circuit test where rated current at rated frequency is applied, I have rated current. I have a rated current. What's the rated current for the system? I have the rated power and I have a rated voltage. So the rated current magnitude, so I rated magnitude in this case, I have I rated, it's equal to this divided by this, 20. That's a magnitude 10 to the 3 divided by 480. The answer will be 41.667 amp. Now, great. I have the power and I have the current. I can find R equivalent, can I? What's the power? P equation is I squared divided by R. Because the real power reflects only because of the resistance value. Great. So therefore, R will be equal to I squared divided by P, which is equal to 300 divided by 41.667. So I P is equal to I squared R. So therefore, R will be equal to P divided by I squared, which is equal to 300 divided by 41.667 amps. Sorry about this mistake. P is equal to, the other one is P is equal to V squared over R. Just please don't get mistaken between these two elements. P is equal to I squared R. So therefore, R will be given, the answer for R will be 0.1728. 0.1728 ohm. Now, how do I find Z? How do I find Z? Great, guys. Look, I have a voltage, I have the power, and I have now the current. What's a Z equivalent? Look, Z equivalent would be equal to V, it's equal to IZ, it's equal to V1 divided by I rated, which will give us 35 divided by 41.667. Z equivalent will be 0.84 ohm. 0.84 ohm. This is Z equivalent. This is Z equivalent. Perfect. Now I have R and I have Z. Z equivalent. So the magnitude of Z is equal to square root of R squared plus X squared. Isn't it? So now I can find what's X is. X equivalent. So this will give me the X equivalent. X equivalent square root of Z squared minus R squared, which the answer will be 0.822. 0.822. That's how now I find this value, 0.1728. This will be J, 0.822. And based on the system now, I can find what's Z. So now Z equivalent would be 0.84. The angle of, now you have R and J, will give us an angle of 78.13 degrees. Is that clear how I used a short circuit test to determine the equivalent impedance, equivalent resistance, equivalent inductance of my system? Now, the second question part of this is, from the open circuit test, determine the shunt admittance referred to winding 1. Neglect the series impedance. Okay. Let's take a moment to digest this information so I can delete this board, and then we will go into the second question. Remember, when we did an open circuit test, what's an open circuit test? If I redraw my circuit back again, I have this circuit. If you remember this, I put a current in here. This is my open circuit test. So basically, all the value that I obtained from the previous one, which is I2, I have I2, 12 amps, 200 watt, is because of the actual shunt. Is because of the actual shunt, which is, in this case, this is RC, this is JXN. Now, because they are in parallel, it's easier for me to recall the admittance. It's easier for me to recall the admittance. When they in parallel, I can call this the admittance of this one, the admittance of this one, and then I can solve it in an easier way, in a very easier way. So what I do is I can recall GC, YM, and BM. So I can call this the admittance. I want to call it GC. I want to call it BM, and the total system for this will be what did they call it exactly? The same name is YM. So from the first one, I have they in parallel. This and this, they in parallel voltage, isn't it? So now I apply the parallel voltage, which is P. It's equal to V squared over R. If you guys remember these equations. Is that clear? So, because now I'm using GC, So it's equal to V squared GC. Remember, all I'm doing is, in this case, I'm using the admittance. So all I have to do is, the admittance is 1 over the resistance. That's why I use this value. So now GC would be equal to P squared P 2 divided by V squared. All I have to do now is, I'm interested in this, so now I have GC is equal to P, which is of this one, divided by V squared, which is equal to what's the rated voltage in here? What will be the rated voltage? Is 480. Because remember, when they said at the beginning of the example, they said short circuit winding now for this one, during an open circuit test where rated voltage is applied to winding 2. When you apply rated voltage on this winding, because of this 480, 120, when I apply a rated voltage in here because of this system, in here I have 480. So across this one, I have a 480. So I have 200 divided by 480 squared. The answer of the system will be 0.000868 Siemens. 0.0000868 S is the unit of the admittance. I can follow exactly the same concept. I can follow the same concept now to find Ym. Same what I did in the previous questions. I can follow exactly the same. What's Ym? I have a voltage V1 and I have I1. Because I have I2, I use the relationship between A and I2, I can find I1. And I go, what's Ym? I just want you to pay attention. What's Ym? It's equal to. In a previous one, V it's equal IR. V it's equal IZ. Is that correct? Now, because you're using the admittance, V it's equal 1 over, is I over Ym. So Ym it's I over V. You have to pay attention to this element, which is give us in this case, Ym, it gives us 120 divided by 480, give us 120 divided by 480 times 12, this is 1 over A, over 480. This value represent the current. And now because I found Ym, I can go and find Vn, and that's how I found the entire transformer characteristic using open circuit and short circuit test. Let's take a moment, let's take a small break, and we can do more examples.